Orlando, Florida. I go to Bishop Moore Catholic High School, and I'm interested in mathematics and computer science.
I'm Joseph Mathis. I'm from St. Louis. I go to St. Louis Prairie School. I'm a rising junior. I'm interested in aerospace engineering.
Hi, my name is Vinay Senthil. I'm from San Jose, California. I'm a rising junior at Lynbrook High School, and I'm really passionate about robotics.
So first, we'd just like to introduce the general product.
So the main purpose of our product is to do application development. So we wanted to make a mapping service which helped in emergency response and analyze past responses. And we expanded this beyond just flood data. So some of us did hurricane data, or tornado data, we did earthquake data, rainfall data, everything.
So throughout the project, the four of us all developed 4 separate apps. But I believe that all of the applications were united under a common theme and a strong set of goals that kind of guided us throughout the process. So throughout, at any given moment in the project, I think collaboration, interaction, and feedback both between us and our mentors and scientists was key.
So our app had a bunch of requirements that are listed here relating to layers and data types. But in the end, what we wanted to create was a meaningful product that can be used by users in an intuitive and interactive way, and maybe hopefully in the future even by emergency responders, so it can be a tool for them. Along the way, we wanted to pick up valuable coding skills such as HTML, JavaScript, and CSS to build our apps. And in the overarching goal, what we wanted to accomplish was gain work experience in CSR and NASA.
So the first step of all of our applications is actually acquiring data, right? We have to have something to work with. So the first major step in this process is scraping data from the National Weather Service, right? So these guys are out there in the field collecting data from gauges all around the country and compiling it. So by a process that's automated by Python scripts, which are housed on the Magic servers here, shapefiles, which are provided by the National Weather Service, which are essentially just data displayed here, which is tied to geographical coordinates in a map. The Python scripts automate the conversion of that shapefile into JSON point data, which is just, well, I'll talk about in a second, which is the actual data that we're able to use in our products. So once, let me go back for a second just to quickly explain. So the REST endpoint is actually what that JSON point data is formatted into, and it's left there, that we can actually access it. As a result of time limitations, this step was actually completed before we reached here, and we're only accessing the REST endpoints. But this is something that goes on behind the scenes that's really important to the actual app functionality. But once it's at this REST endpoint, that's essentially it's waiting to be queried. So using the Esri REST API, which has a maximum return limit of only 1,000 returns for any given call, that means it can only give you 1,000 data points back for any question that you ask it. So to get actual data from this, right, you have to go through this interface. You have to specify what kind of data you want. You can either query by value, you can query by geography. So you also have to tell it what you want to get out. So once you've specified all the queries, you can get raw data available in several relevant formats, including JSON, which that just stands for JavaScript Object Notation, which is a couple big words. Another big word, it's just a formatted object literal, which is a type of object in JavaScript that basically holds data in kind of a nicely formatted way. So this is obviously probably not readable to a human, but at least looks kind of nice, and you can tell that everything has labels and key value pairs. And GeoJSON is optimized for online use in mapping libraries because the critical element of it is geographic coordinates. So you can tie numbers and rainfall data to points on a map, which is what we'll all be doing in a second. This is also a humongous and scary URL here, but there's only a couple important parts here. A lot of it is just syntax that's necessary for the call. But the first thing we have is specifying those queries that I was just talking about. So when I say glob value is greater than 0.1 inches, I'm asking the REST API for data points that have rainfall above 1/10 of an inch. That's all I'm asking for. Everything that's highlighted in green is geographic specifications. I basically made a 1x1 degree box of latitude and longitude and asked for it to return that in there. So in our code, we can take user input and specify specific geographic coordinates that we can then push to the API.
So the next part is how do we set up our map? And what we do is we organize it into layers. And why do we need layers? Well, what's the purpose of maps? We have maps to organize spatial data in a way that can be easily understood by the reader. But because we have to limit data types to a limited amount. Because if a human could understand tons of data types coming at it from a map at once, we wouldn't need more than one map. We'd have all the spatial data in the world on one map. So this type redundancy makes us need groups. And the way we use these groups in digital mapping is layers. So what a layer does is the base map will show you the ground layer, so like just the Earth. And then there'll be data layers, like the precipitation data here, which go on top of the data. And then we heavily use the Leaflet Library, which is a JavaScript library. And the reason we need a mapping library is because a digital map shares, all digital maps use like some capabilities. They'll like add layer, folding layers, they all use that. And it would be a huge waste of time for everybody to have to code that again and again and again. Not to mention it would limit the amount of people who can actually do this mapping because it's really hard to do this. So the advantages of using Leaflet is that the common functions are already there for you. And that means that you can code faster, there's stronger cross-compatibility. So if I want to combine two people's maps, it would be easy. There's multi-platform, so it's easy to use on your phone or on your tablet or on your computer. And it's more readable for someone who doesn't know your code personally. Map building. So we use jQuery to receive data, and it's difficult to do in JavaScript without an external library, and allows us basically just to fetch the online data that we need. It also helps us dynamically change web pages. So we have a web page that's already loaded, and we want to change like an attribute of it. So we use jQuery to listen for something and then change it. We implement these changes to the styling attributes with ease. And then JavaScript is how we process the data that we've grabbed with jQuery. So it's basically the brain of the map. And then with JavaScript, we basically control the workflow of how the map works. You can see the workflow right there. Basically, we grab the data with JavaScript and jQuery, we process it with JavaScript, and then we display the data with JavaScript and Leaflet into the map. And then there's some other styling stuff going on the left, and every time you use jQuery to interact and grab more data.
Alright, so what we've been talking about in the past few slides are all the code and the behind the scenes. But what really matters is how we display this information on a really interactive and intuitive user interface. So what we can do is add, using the Leaflet library, is add markers, polylines, polygons, circles, and pop-ups, and more like interactive buttons and stuff. So here are some examples of the circles, markers, and polylines. And what you can do is have the user interact with them. And in fact, you can also download other stuff from the internet, downloadable software packages such as Mackie Markers, Font Awesome, to customize it. So you can see on the picture on your right, there's a lot of different images representing different natural disasters. So there's like a windmill for the wind, rain has like rain and water, I guess, and then hail is the snow. And so basically you can customize your app to how you want it to look. In addition, inside pop-ups and polygons, you can insert graphs and images. So here's a example of a pop-up, and then using a different API, which is like a coding package that you can use to code different stuff. You can insert graphs and images into pop-ups. So it really makes it a really dynamic website. So now looking at CSS. CSS is a coding language, stands for Cascading Style Sheets. So when you're coding HTML, you're making objects in your web page. So you're making a div, a header, a footer. But CSS comes in and helps beautify those stuff. So you can add different properties to it. So you can add opacity, color, text color, position. So you can, that's where all of the attributes for that object come in. And so all of those different properties right there under show button make that one button called show and hide tornadoes. So you can see there's a lot of different ways you can customize your buttons to make it look really cool. So in our case, we use it to make our legends, general formatting, sidebars and menus, pictures, and also what you can do with CSS is make your website look really responsive. So for example, if I like hover over that button, it animates to look like I'm actually clicking the button, or you can, and it also allows you to make cool transitions between different things. And so once you have the user interface set up, now you have to make it really interactive. And so the way we can do that is adding event listeners. So what an event listener does is it's always a continuous function that runs in your code that looks for specific actions that the user can do. So in our case, since we have a map, it can be clicking, hovering, or dragging. So whenever these event listeners are activated and the user initiates something, we call a code which is called a callback, and they're asynchronous, which means that some other code could be running and this one could be running as well. So there could be two functions running at the same time. So event listeners also don't need to be physically written down. So for example, if you want to create 1,000 event listeners, right, you don't need to physically write down all 1,000 of them. You could just use a for loop and just create 1,000 different event listeners, and then those will all be stored on the log, in the program's log. So they all don't need to be written down. So that's really cool about event listeners. So now looking at layer toggling and user query. So in our map, we really wanted to make it interactive. So whenever the user clicks on a map, for example here, it can show the elevation and location by querying the coordinates of where the user clicked to an outside website, get the information, and then bring it back and display it in the pop-up. So that's an example of like user querying. And then if you want to look at layer toggling, this is an example of like a nav bar that would like turn off and on different layers. So you can turn off like the pop-up layer, the polyline layer, and that's an example of QPE data. So for example, the code snippet to activate these is like a map.onClick and then do your certain the function that you want to do.
All right, so some of the final touches we had to put in were basically making the code readable and accessible to other developers and to other platforms. So that means clarifying code for developers. So basically comments. You can see anything that's in gray here, it's preceded by an exclamation point and 2 dashes and ended by 2 dashes. That's a comment. That's code that isn't actually run by the compiler. It's just there so that you can read it. It basically says what the next block of code will do. Another way you can do that is spacing. So you can see everything's on a separate line, and that will separate all of your elements so that someone isn't going through a line that's 800 characters long reading all of your elements. As for mobile, this also is for basically the CSS, your style sheet. You have to account for the fact that when you're displaying something, if you're putting in coordinates on the screen, you're not always going to have a screen that's the same size. So sometimes you'll have a screen that's like that big, and it's landscape, and it's portrait instead of landscape. So you have to account for that in your CSS depending on what platforms you want it to be available for. So the next thing we had to figure out was web hosting. So our code is actually hosted on the Magic servers with live URLs. And that's basically, it has this in the browser text box instead of a bunch of strings of numbers like it would be if you were hosting it on your home computer without a domain. And that's called a custom domain. We also use GitHub in the GitHub platform. It's an open source website. It's a website that allows you to put your code on a repository that's open source. Anyone can grab it. Anyone can use it. They can make forks and edits. So this uses a command line tool called Git, and we have that right here. That's basically, it's a command line tool. You use it to add files to your repository. GitHub is the file server that it's on. It's the website. And RawGit was actually a utility. It's a website also. It's a utility that we were able to use for prototyping our websites.
And so at this point in the presentation, we're about to go into our individual products and then demo them for you guys. So I'll start off talking about my application. So the goal of my app was to evaluate real-time flood risk in Texas. And in addition to that, I also wanted to use historic data in an effort to improve future response. So this manifested itself in primarily incorporating live flood gauge data, which is provided by the National Oceanic and Atmospheric Administration's National Weather Service. They have a procedure called the Advanced Hydrologic Prediction Service, which essentially deals with water and flood gauges in this sense. So they provide hydrographs and other information about the status of these gauges. So my application has links and references to all of these data that it provides. In addition to that, I also include archived rainfall data from April 19th, 2016, which, as many of you know, especially those who are in Texas, is in response to the major flooding event, especially in Houston, where over 7 deaths, 1,000 homes destroyed, and $5 billion in damages were recorded in the city of Houston alone. So I'm providing rainfall data in 2 different layer types, both raster and vector, which I'll explain in a little bit. But in the effort to hopefully analyze the response, that was actually how it actually went down in real life and how we can maybe improve upon that in the future. So I'll actually go into the website now. All of these are live. If any of you were to access this URL on your phone right now or on a laptop, it would work. It would be fully functional. So the colorful thing that you're looking at right now that resembles what you would see probably on a classic weather map is QPE data. It's a raster layer, which basically just means it's a big grid of images. So that's not actually interactive at all. It's basically just displaying images, obviously with the transparency over this map because you can still see underneath it. You can see here's Austin over here and Houston on the other side. So this is essentially just cached images over the blade, which means that they're saved somewhere and then just displayed on the map. But if you actually want to find more about the actual rainfall data, because you can look at this legend over on this side, you can say, oh, that color kind of resembles this. But the better way to do it is actually to include vector data. So vector data actually has specific values and points and geographic coordinates. So the way I've designed the app is if you click in any specific region, it'll pull up that one box of degree, latitude, and longitude that it actually has all of the point values for it. So now if you were to zoom in and you want to see what the value is at this point, it'll have the ID, the location of the gauge, or of the estimate, and then the actual QPE, which is, it stands for Quantitative Precipitation Estimation. So that's basically just a total estimate of the rain that actually fell in that area. So you can zoom out, and the interactivity of this is obviously you can query as many specific boxes as you want, and you can get as specific as you want. You can reset those. At any point you can hide the layer completely. And now, so the only problem with the raster data is it makes the other layers slightly difficult to see. So if you're really just interested in the flood gauge data, you can hide that and then look at the flood gauge data only. So these flood gauges are coming directly from NOAA, and it has all of this data about exactly what's going on, right? So this last stage report, 26 feet was the report here now. And now we've got the hydrograph here, and this is live. This is a link to an image that's regularly updated. At 4 p.m. Thursday, July 28th is the next coming up, so we're right there. And if you click on this gauge ID, it'll actually take you to the weather.gov page, which contains all of the data about the gauge. So obviously I'm not going to be able to provide all of the information that someone who would actually be providing a professional service on a small little pop-up on a leaflet marker. So that's why I provide the link to get to the page. So we can bring back the QPE layer. Any information you're wondering about is displayed in the legend and rainfall legend. And then lastly, if you click anywhere that's not rain, obviously there's not going to be rain forever all over the place. So it'll tell you that there's no rain in that location. That's about it for that. So I think there's a lot of challenges and a lot of solutions that we had to go through in just making that product. So coming in, I had almost no experience in HTML, CSS, or JavaScript, which are the 3 languages that website is written in. So there's certainly a learning curve for that, as well as for the libraries that we're also using, which is where a lot of just persistence and stubbornness came in, because if you really just put your mind to it and do not stop until it gets done, it'll get done. I think a lot of cooperation between us was also helpful in that, especially when we were dealing with issues like improperly formatted GeoJSON data, where one provider of data was putting in a slightly different, it was the same object type, but the actual structure of their data was different, the architecture was different. So we had to go through and skin each of the data types to actually get it to force it into what we wanted it to be so we could actually use it with Leaflet. That was frustrating. There was complications regarding custom markers, downloading more APIs to try to get additional functionality. Naming conventions and file paths were often non-clear for a lot of the sources that we were using, or I was using. And then pushing to open source was something I'd never done before, which is something that I also learned how to do. API documentation was huge. So an API is basically, as Vinay had mentioned before, it's just like a package that someone has written that does a lot of things for you. So you can call these people's methods that have been written out on the internet. Usually the ones that we use are fairly reputable, that are used fairly commercially. But with any API there comes documentation, which is essentially that developer wrote an explanation of what this function does. So that allowed me and the rest of the team to get a greater understanding of what our function calls are actually doing, because we're calling a function that actually goes down another level to that code. So it builds back up. If we have a better understanding of the base, then actually that builds a better understanding of your actual code and then website that we just saw. So a lot of creativity was necessary too. This is a shame because I often logged over 1,000 errors to the console, but ultimately there was no actual errors, so I had to go back and make some for the purpose of an image. But this looks much less scary than it did sometimes when it logged 1,000 errors. If you have an error in a loop, it just looks really bad. Hand over to Joey.
All right, so my project goal was basically to consolidate various types of emergency data into one interactive map. So that means rain, earthquakes, hail, damaging winds, whatever. And so I also wanted to provide info to any users about the specific event. So if there's a tornado, you want to be able to find out the intensity, the location, all of that. And I wanted it to be as user-friendly as possible. So I'm going to actually demo that right now. There it is. So you can load it up, and again, this will work if you type this URL into your phone, tablet, laptop, whatever. So it has this little thing here that tells you how to use the app. So I'm going to dismiss that. So you can see you have all of these different markers and the legend telling you what all of them mean. You have all these buttons on the side, so if you just want to focus on hail, you can, hide everything except hail. There we go. So then, if you zoom and click on one of these, it'll say, state, county, location, all that. And then some of them have comments. So this is useful if you're going to go driving somewhere, you want to check. Oh, that's great spelling there. So this is pulling live off the internet every 24 hours, although I'm actually showing you yesterday's data. If I were to show you today's data, there would be nothing on it because there is no hail today, apparently. So yeah, you can just kind of go through all these, and so that's useful for emergency responders if they have reports. This happens a lot with the wind. See a tree down on power line on fire. So you'd be able to look at that and then go and fix the tree down on power line on fire. So yeah, that's kind of useful for that. Also down here I have a precipitation amount forecast. This is just an image from NOAA, and that'll tell you the amount of precipitation in a given area that's forecasted for the next 24 hours, and that is the chance of precipitation. Yeah. Now we'll go ahead and head back over here. So some of my obstacles were that I had never actually used JavaScript before, which is basically the main scripting language for all of the objects on the page. I couldn't really find a lot of live data in a usable format. So it would all be in KML or some other format that we can't actually use with this program. And so I had trouble finding data. And then when you found data that you could actually convert to a usable format, I had some trouble converting that. So I'd find CSVs and I had to write a bunch of functions to convert it to data you can actually use. Also differentiating between sets of data, hail, earthquake, all of that. Originally I had it set to circles, and they were all just, you'd click on a circle and you'd have no idea whether it was hail or a tornado or anything until you actually clicked on it. So I had to use custom markers for that because Leaflet doesn't have enough stock markers. There was also a learning curve of Git and GitHub. It was really hard to actually figure out how to use the command line tool to push all of your data to an open source repository on the internet. So that was just kind of the things I had to get through to actually finish the project. So I'll turn it over to Vinay.
Alright, so my web application is based around earthquakes because I'm from California and earthquakes are a daily part of my life. So the why behind it. So earthquakes are now a really major earthquake in a highly populated area can cost over $200 billion in losses. And the fact that earthquakes are not just the damage causer, they're also floods, tsunamis, and fires that are caused by earthquakes. And you might not know it, but there are over 50 earthquakes recorded in one day. And the real reason why earthquakes are really deadly are because that they occur underground. So they're unseen forces. They happen with the tectonic plates. So there's not really much information about predicting them. So the goal was to create a world map of earthquakes that have occurred in real time in the past days. So thankfully, since 50 earthquakes happen every day, my map's pretty populated. Then I'd like to also create intuitively display that information so you can see the magnitude of the earthquake, get more information if you like. And in addition, I also added the different fault lines that occur across the entire world, and you can find more information about them by querying their elevation as well. And I wanted the user to also query information to find more if they need to. So now I'll give you a quick demo. Alright, so I creatively named mine Eagle, Earthquake Analysis GIST Layer Engine. So basically, so let's get started. And then, right now there are 3 main layers that you can see. There's actually a fault line layer, which is all the ground lines. And then there's the earthquake location and magnitude view. So if you click the earthquake location, it'll tell you exactly where the location happened, the magnitude, and the time. If you wanted to, let's say, close it, you could also see, just click the magnitude, which actually shows how far the earthquake actually affected, and you can see the magnitude. And so you can turn all these on and off. So you can see a little bit of CSS at the top, as I hover over these buttons, they change color. And then another cool feature is that if you wanted to like just check for elevation anywhere in the map, you just check this button.
Move it up a little.
Yeah. So you check the button, and then now if I start clicking anywhere, it tells me the elevation of that place. So yeah, that's pretty cool. And so if you turn on the fault layer, well, another really cool feature is that if you click the fault layer, you click for a graph, and then 2 seconds later, it draws the elevation of that specific fault line. And so since there are over 4,000 different fault lines that I have on my map, it's really a pain to like generate all of these, and I'll go over how I fix this problem later. So all of these are all color-coded on the color-coded thing on the side, and yeah, that's pretty cool. Yeah, so that's that. Alright, so the problem that I had in making this was, when I first came into here, I really thought there was going to be like an earthquake API, so I could just like get all my data just like that, really simple. But apparently it doesn't work like that. You have to actually query stuff, and I really learned that the hard way. You have to get elevation from this certain link. You need to get location, use reverse geocoding, a bunch of different things to get all the data that you need. And so that's what I learned for there. And then in the beginning was layer toggling. Just turning that layer on and off took one whole day. Just like figuring out how to use jQuery and using Boolean statements. And yeah, so I figured how to get layers to toggle on and off. And then creating the graph of elevation. So as you saw, there like, as I mentioned, there are like 4,400 different fault lines. And so if I first load my app with all graphs loaded, the web application will probably crash and you probably never see it. So what I'd have to do is I had to use inline JavaScript and use event listeners that are generated. And the event listener waits until you click the click for a graph button. And then when it does that, it requests more information about that specific plot line that you clicked and generates a graph on the spot. So that's why it takes 2 seconds after you click it. And then I also had to learn about waiting for queries to arrive. So when you're querying, you're actually limited to how many queries you can do per second, depending on the API. They want to make money, right? So they have like different plans that you can do. So you can get 50 queries per second, 100 queries per second. But I'm stuck with 1 query per second. So what you do, what you have to do is actually wait for the query to come back and arrive. So I actually learned this the hard way. So I'll be coding, running the program, everything looks nice, and then it'll be an undefined variable, undefined variable. So what it turned out was happening was the rest of the JavaScript code would keep running, and then that function that was requesting query would not return in time. So yeah, what you have to do is like wait for the function to be ready and then continue on. So using more jQuery. And then finally determining where you're clicking. So as you can see in our maps, we all have many layers. And so when you're clicking pop-ups, even if they're, like as you saw the elevation pop-up and the magnitude pop-up, if I clicked on the magnitude, both would show up. So I have to fix this with using checkboxes and turning on and off layers.
Okay, so my project focused on rainfall, and basically rain rapidly increases your chances of getting into a car accident. I mean, it happens during floods, hurricanes, and it's the 5th largest cause of car accidents. There are a lot of existing maps for rainfall currently, but what you don't think of checking is where did it just rain. So slickness is actually one of the huge dangers of rain. So my solution was to create an app where you could give it a route that you're going to take, and it tells you the slickness along that route. It allows better positioning for first responders, so they don't have to just position themselves based on where it is raining right now. They can position themselves based on where the roads are actually slick. And I utilized Open Weather Map and the National Weather Service Weather Mosaic. So I'm going to demo now. So I have this opening message that tells you basically what the app does. And if you don't have this, people don't realize that this will help you on the side here. So it's pretty important. So what I'm going to do is I'm just going to draw a basic route. I'm going to go from San Antonio to Beaumont. And it shows me that the first segment of the route, there's no rain. But then later on, it gets to be between 0 and 2.5 millimeters of rain. So that's something you should just look out for. And then you could try another route, so like San Antonio to Victoria, then through Houston again to Beaumont, just to compare the differences in rainfall along the routes. So you can also change things like size, especially if you're on a mobile device. It's really important to be able to make the lines really big, because if you click a certain segment of the line, it'll tell you all the important data about it. So it'll tell you the place in which it's based, it'll tell you the current weather right now, and it'll tell you the rain level and the last update. You can also change it to a different edit mode. So right now I can query a certain point, like Alexandria, there's no rain there. And I can toggle whether or not I have points available, the legend available, and routes available. So as you can guess, I too had a lot of challenges while making my app. I had incompatible data formats, which basically means they both gave me JSON data, except they gave me coordinates, and one gave me the latitude and then the longitude, and then the other gave me the longitude and then the latitude. I didn't realize that for a very long time. But what you find is if you're trying to map flood data in Texas, and you change the latitude and the longitude, you're then mapping flood data of Texas in Antarctica, which is kind of a problem. So yeah, what I had to do is I had to create a GeoJSON format and basically make a uniform data, which I converted them both to, which wasn't really fun, but I had to do it. So the next part was for the API I was using, Open Weather Map for precipitation data. They only give you 60 queries per minute. And that can be even more of a problem because I use 20 queries per path. So that gives me 3 paths per minute. And that just wasn't going to fly. So I made my app open source, and then they agreed to give me unlimited queries after contacting them and asking them very nicely. So their API does have limited search capabilities, though. So if you're using any of the APIs they use, mostly they give you can put in input geometry. So you can give them a polyline, and they'll tell you where on that polyline the data lies. But they don't do that, so I have to split the routes into segments. So I did 20 equal segments, and then I based the data on the midpoint of each segment. And then they also had inconsistent database practices. So half the data is given for the rainfall in the past hour, and half the data is given for rainfall in the past 3 hours. And there's not really a win-win situation on how to deal with this. So what I just did was I converted the 1 hour to 3 hours by multiplying it by 3. Because my view is that I'd rather give them more rainfall than there really is, because it's better to over-prepare, I guess, than to under-prepare. And then they also had illegal variable names, which I have no clue why, but they decided, hey, let's start our variables with a number, because you can't use that in JavaScript. So yeah.
Awesome. So now we're going to move on, and we're just going to reflect on the overall process.
Okay, so if we had more time, and I don't know about you guys, but I actually plan on kind of extending this once I get home. I think one of the things we could do is we could create our own REST endpoints from shapefiles using Python scripts like we already discussed. That was already, we had to use basically REST endpoints that were already available, so that sort of limited the data we could use. So that would allow us to have more sources of live data or whatever type of data you want. Also, we'd like to be able to specify modes of precipitation, so you'd have like a separate layer for snow, hail, rain on your precipitation maps, like the chance one I had on mine. Because right now it just says precipitation, so you don't know whether that's snow or hail or sleet or raining dogs or something. So, I mean, it could be. But anyway, yeah.
Alright, so also what we wanted to do is add increased mobile functionality. So most of our stuff are coded with using CSS are coded specifically for our own laptops, or we at least tried to make them a little bit functional. So they coded to our laptop. So if you open them on your phone, for example, you'd see the application, but it'd be really hard to navigate. So all we want to do is use Bootstrap, which is a form of CSS that allows your website to become responsive. So if you opened up the app on your phone, it'll automatically adjust. I mean, you have to do a little work, but it'll automatically adjust it for you. And then we'd also want to add enhanced graphical visualization. So maybe you can animate some of the polylines and figures, and if it's actually raining, show like a raining animation or something cool like that. And also what we want to do is add user-defined polygon query interface. Now that sounds really complicated, but basically you just want the user to draw like an area they want to specifically get queries from, and like it zooms into the area and gives you like information. And then another cool thing we want to do is add get custom domains for each of our stuff.
So as far as the overall program goes, I think all four of us gained a lot of valuable insight into web app architecture because we were actually going in and hard coding the foundations upon which our applications were based, right? It's all of you guys just saw the upper layer, right? That's like the absolute final product, which has almost nothing. It looks nothing like the hundreds of lines of code that are all behind the scenes, right? So I think we gained an appreciation for like how complicated and like how complex the interactions between different types of codes, different languages, different APIs and libraries all interact behind the scenes to give you like what you actually want. And like I know my website ended up being very simple. Like we all have pretty like singular functionality, but like all of those functionalities are very difficult to achieve and are actually I believe they're somewhat impressive in like the amount of time we were given. And so it was also really cool to be able to work in a software development team, even though we were developing separate apps. It was definitely still a team project because we all helped each other out and we're working towards similar goals in the end. And we were also able to apply programming and data analysis skills to actually produce real, legitimate scientific return. Because I feel like in these products, which are obviously just web applications, I feel like they are doing a sort of science that is actually important and valuable to people, which I think is pretty cool.
I mean, it was a great feeling to have that, build a program, and you have data, and the user's like, I want that data, and I can actually give you that data. So, and then having a timeline for objective completion. So usually when I'm programming something, it's just, I'll do it whenever. But when you're doing it on a team, like you have to do fast paced, you have to build this stuff, build this stuff, build this stuff. And it was really cool actually to have like that pressure almost.
Alright, so our final reflections are that throughout this project, we gained exposure on Earth and space research, and we also got an interdisciplinary field. So we got like geology, meteorology. We brought this all into computer science, then displayed it on like a web application. So we learned a lot of different skills that we can use, and we also learned a lot about analysis and visualization of data. Because only if it looks good, like people would want to use it even more. So we learned a lot in those kinds of areas.
And then we actually get to complete like authentic research and meaningful product. Like everything that we built actually does something. It's not fake. We're not hiding anything. And I feel like that we actually enjoy STEM more, if that's possible, than we did even before. It's just like a love that just keeps on growing.
And throughout these 2 weeks, we were really given an in-depth glance into the aerospace engineering field, as well as the nature of essentially every other engineering major and all of the STEM fields as an area of study in general. I don't know, I felt like we found a lot of clarity in that as we worked through our processes and saw everyone else working and heard about their presentations and heard lectures from various professionals from all of their fields. I thought that was really special too.
Yeah, so also we made some great friends here and forged professional relationships, not only with each other as a software development team, as interns, but also with our scientists and mentors. It also had a profound impact on our mindset. And so it's helped us kind of have a more success-oriented mindset where you have a task and you have to complete it. And it doesn't matter how it gets completed. If you have to ask for help, if you have to use an API that is kind of weird, whatever you have to do, you just get it done. And you have a deadline, so you have to do it. It's not something you can do whenever. You have to do it. And so it gave us that mindset of, you have to have results, and results are what you aim for. And it doesn't matter what it takes to get there.
All right. This may be the most important slide of the presentation. Before we finish, all of us just want to thank everyone that was involved throughout the process. We would not have been able to do it without especially the hard work of our mentor, Mr. Brent Porter. We think we should give him a round of applause. He's a real talent. We're doing our best over here. We also want to thank Ms. Baggio, everyone else who worked with us, who stayed with us in the dorms, who was making everything we did possible, because it was truly a special experience. I know for me, like, one of the coolest things, it's kind of, I guess everyone agrees, that going to Johnson Space Center was, like, truly awesome. Like, I was just kind of, like, mouth agape for, like, most of that. It was like, truly amazing to, like, see this actual, like, real-life place where people are doing real-life science and going, like, to outer space. And they're like, yeah, this is my job. They're just, like, chilling in mission control. Talking to ISS was really interesting. It was just like, I could have sat there all day and just watched these people, like, hit a couple buttons on the computer. It's like, it's the most fascinating job of all time. I don't know. So I'm really grateful for all of the experiences we were able to have.
I mean, it was just truly fascinating. It's definitely one of the highlights of my summer, the highlight of my summer. The work that everybody does behind the scenes. I remember Ms. Baggio talking about her husband working 8 hours getting the wood for telescopes. It's just crazy. Just amazing. I was really impressed with the JPL, not the JPL, oh my gosh, the JSC too.
Next time,
yeah. And just the fact that we worked on a team, I feel like our products were so much better because everything that we did together, it was, when one person figured something out, everybody figured something out. And it was just great.
Yeah, this experience at NASA was really eye-opening. I got exposed to a lot of new different fields, like the meaning behind aerospace engineering and how it was such a cool field. But the really, one of the really cool experiences I had was actually at the robotics lab in JSC, where they actually had a rocking autonomous robot trying to climb over the steps, the Valkyrie robot, and it was really cool to see that maybe the next generation of space flight is going to be with the robot behind you, protecting you, or getting data and stuff. So it seems really cool to see the next generation of space.
Yeah. So I'm also really happy I was able to do this. So I'm really grateful to everyone that made this possible. I think just especially going to the neutral buoyancy laboratory was really eye-opening in a way that, you have divers, you have astronauts working together. That's about, the bottom of the ocean to space. That's about as far away as you can get for working environments, and they work together in the same place to do really cool scientific research and training. So, yeah.
So we'd just like to thank all of you for the last 2 weeks.
Yeah, thank you so much. We're so grateful.
We hope you have some questions.
I have a question. So what kinds of tools do responders use now? And why is the tools that you guys are working on, how will they improve on what they're doing now?
Okay, that's a great question. So I think currently we don't have a specific background in this, but I think emergency responders now are using a lot of that federal type data from the National Weather Service. And I think the way that they interact with it is pretty diverse. I don't know if there's a standardized method of going into that. I think what makes our applications different is just the manner in which we present data. I know that Spencer's, talking about slickness is not something that I've ever heard of before, right? Because past rainfall is often something that we don't think about. We're looking at those weather maps of those big tiled raster layers moving over, and you're like, oh, we're in the clear. There's no rain over us. But that might not actually be safe, right? And looking at historical data, I thought was something that was interesting because that's not something that current emergency responders would ever look at. But I think that's something that behind the scenes, not an emergency situation, but you're looking at analyzing and improving basically just your response tactics, I think would be something that would be interesting to interact with. Yeah, Alex.
Well, mine is more of a comment than a question. I just think all of your websites look pretty sweet.
Thank you.
Yeah.
We appreciate your kind words. Anybody else? Yes.
Can you give an example of a eureka moment where one of y'all figured it out and everybody else was able to benefit from it?
So 3 of us had an Antarctica data.
Yeah. I accidentally scrolled out of my webpage, and
we found it by accident. Joey was the only one who
was
was
the only one who didn't get to see data in Antarctica.
Yeah, it was a really funny story because Spencer, he was the one who found it out first after spending some time on it. Then he told Gabe, and I was just overhearing that, and I was like, that's never going to happen to me. And I was like, I'm going to watch out for
a day later.
And then the same day,
I
think me and Tom were working on it for an hour.
Tom stared at this code for 90 minutes. He's like, nothing's wrong with it.
And then we consoled the log, everything, and then I was like, God, can you just hold me?
I'm like, do a scroll down.
Scroll down. I scroll down, and then it's there. Yeah.
Plus, yeah, and then we found a lot of information about API calls and actually writing functions that worked and called actual things. Syntax, a bunch of syntax.
Any other questions?
I have an observation. I think that some of your tools are a couple of generations in advance of what some of the federal websites are using, especially the National Weather Service. It's much more intuitive and much more interactive and gives immediate feedback. And they're very conservative when they make changes, but you would hope that they would go in the direction that you demonstrate.
Thank you very much.
Thank you.
Good job.
Yeah, wait, Carl. Carl had a question.
Oh, it's just line numbering.
It's binary.
Yeah.
Yeah. Thank you.